DiBlasio. I am a junior chemistry major here at Wofford College, and this past summer I had the opportunity to work with Dr. Harris and a couple other fellow chemistry majors looking at the development of a zinc aminotroponimate ligand for hydroamination. So what exactly does what I just say mean? So hydroamination is a type of functionalization reaction in which we're creating new carbon-nitrogen bonds. So the figure you see on the top right shows a carbon-carbon double bond or an alkene reacting with a nitrogen-containing amine, forming a carbon-nitrogen bond. You see that double bond breaks to form a single bond, but one of those carbons attaches to the nitrogen via reaction with catalyst present. So hydroamination is a very well-studied reaction, especially over the past 15 years, as it has a high atom economy. It's basically a very efficient reaction. You can see there's only two substrates being used and a catalyst, which is remade at the end of the reaction, can be reused. So a lot of these catalysts in the past for hydroamination have used either expensive metals such as gold or toxic metals, and we decided to look at zinc for our work because it's both cheap and non-toxic. And like I said, the overall goal was to synthesize a type of ligand with the general structure of a aminotropinamate with a zinc metal attached to it. And those two ligands you see up top with the isopropyl and cyclohexane groups are ones that have been made previously, and the ones on the bottom row are some that I attempted to make during my research. So what exactly became of my research? Unfortunately, I was not able to make the catalyst that I was hoping to make. However, I made lots of good progress attempting to make it. One of the cool progressions I made was creating a new compound that has not been included in any previous publications, and that's that 7-membered ring structure with the two paramethoxybenzyl groups in the top figure. So while that's cool, it's not really that useful. What would have been very useful is if I was able to generate the product you see on the bottom figure, that free amine version of our ligand precursor, via cleavage of those PMB groups with TFA. And while the reaction did work, and could then just be and then you could just tossylate the amines in order to generate the ligand precursor, I was not able to get the free amine precursor for the ligand in high enough yield, and it was also very impure, as this was a multi-step synthesis, so it was very important to get each reaction to have a nice high yield, and unfortunately I just couldn't get this reaction to work that way. So what exactly did I learn from this experience? I've had two main takeaways. One was I gained a lot of laboratory experience using cool chemistry equipment such as a rotary evaporator, a Schlenk line, which is really cool. That's what's going on in the right picture. The Schlenk line's out of frame, but it allows you to perform chemistry in inert atmospheric conditions, which is very useful, especially with our work, as we dealt with lots of chemicals that are oxygen sensitive. So we also learned column chromatography, which is that cool looking colored thing on the left, and that allows you to separate products within a reaction vessel based on various properties such as polarity. We also learned other forms of purification like TLC, and we also learned NMR and other things. And then another skill I gained was interpreting scientific literature, as we would have literature reviews, and that was very helpful because chemistry papers can be quite dense sometimes, and it was useful to see how a a chemistry PhD looks at those papers. So that is what I learned and gained from my experience this summer.